My name's Ben Hamner, and I run the internal science and engineering groups at a small San Francisco tech startup called Kaggle, which many of you may be familiar with for running public-facing machine learning competitions. And more recently, we've also focused on doing a lot of predictive modeling and machine learning work for the energy industry. But I won't really be focusing on that at all in this presentation. And this will be a bit different from a standard Strata talk as well, where normally someone will come up on stage and talk about all the things that work well in machine learning or a really cool application of machine learning or data science they're working on. And then you can go later on in the evening and buy them drinks at a bar and see all the things that didn't work well in the progress of this work. I'm actually flipping that in his head and saying all the things that didn't work in machine learning in this talk, and then later on, if you grab me afterwards, I'll tell you a bunch of success stories. So I want you to walk out of this room at the end of the day with just 3 simple messages. The first is that machine learning is powerful. The second is that there are many, many ways to screw up and mess up machine learning, and this is what I'll really be focusing on. And the third is a piece of good news in that all of these are avoidable. So as long as you're careful and ask the right questions and are constantly measuring your performance, you can avoid these. So first, I realize I'm really preaching to the choir in this sense, since the fact that you're sitting in this audience means that you already believe machine learning is powerful. But I just wanted to share 2 examples of machine learning I've worked on in the past that are some of the favorite projects I've worked on. So for the first one, this is a brain-computer interface system I worked on a couple of years ago at a university in Switzerland. But the really cool thing about this is that I'm imagining moving my left hand or imagining moving my right hand, and through that imagined movement, not actually executing any movement, but simply imagining movement, having this wheelchair turn right or turn left, and thus I'm able to control an external device without actually needing to move anything. So this was a really, really cool system, and at its core, it's enabled by machine learning, and this system wouldn't function whatsoever without using sophisticated signal processing and machine learning algorithms to detect what my neural patterns look like, interpret them, and then classify them into a left class or a right class. And then a second and more recent example is one that we worked on in the context of a Kaggle competition a couple years ago, where we worked with about 30,000 student-written essays, and we challenged our community to go through and automatically grade these essays. We gave them both the underlying text of the essays as well as 2 scores for each essay from a human grader or graded by a teacher. Now, one really interesting thing about this is, of course, the teachers weren't 100% consistent with each other. They disagreed on what some of the grades should be, and they may have had about an 80% level of reliability. And it turns out the best machine learning models that our community created also had about an 80% level of reliability with any of the individual teachers. So this had the very surprising result that the machine learning methods were just as reliable or disagreed just as often with the teachers as the teachers did with each other. And with that, before I really dive into some of the examples of where machine learning's gone wrong, I want to give a brief high-level summary of what a machine learning process looks like. So first, we generally start off with a business problem like decrease churn by 2% or build a spam filter, or a charitable problem such as automatically grading these essays. We need to go and gather some data. We need to split the data set into a training, validation, and test set, or have a strategy for splitting the data set. We need to choose an evaluation metric or evaluation metrics. So how do we judge how well we're performing, which isn't always simple and straightforward. We need to extract some features from the data so we can use the data as inputs to a machine learning algorithm. Then we need to actually go through and train a model, select the best features to use in the model, select the best models, and then finally apply this into a production system. And of course, this is more of an iterative process in a loop and not a completely linear process. But the reason that I'm walking you through some of the basics at a high level is there's gremlins that can arise in every step of this process, or things can go wrong and break in every step of this process. And to illustrate that, I'm going to take a moment to walk you through an entirely hypothetical case study. And so my friend Sarah runs a pet door company, and she wants to bring the pet door company into the Web 2.0 era and the Internet of Things by making it intelligent. More specifically, she wants to let this cat in, but keep this dog out. So I'm thinking, okay, great, that sounds like a machine learning problem. That's something I can go and help you out with. The first thing that we need is to go and collect some training data. So I'll give my photographer friend Adam a call, who's taking a lot of pet photos, and ask him to send me some over. He sends them over to me, and then I take a sample of them. They look like this. There's about 400 of them total. And then I go ahead and load them up into my system. I train a machine learning model over those, and I see how well my machine learning model does on the training set. And it turns out I get 100% accuracy on my training set. Now, anytime I see 100% accuracy or a 0% error rate in machine learning, I get nervous because that almost always means something is wrong. And in this case, I take another picture, in this case, one that I had of my dog Luna. I throw it through the system and then make a prediction on it. And what do you expect? It tells me my dog's a cat. So in this case, this obviously is an unexpected result, and I want to go and start peeling back the magic and looking at how the system's working. In this case, the system's training over a set of epochs. So I can look at my training error. So the y-axis is my error on the training set, and the x-axis here is my training epoch as the training progresses. Then naturally it starts off not being able to distinguish cats and dogs at all, and then training progresses, and I get better and better and better until I get almost perfect on the training set. However, I've not been really principled here. Instead, I should be making my evaluation on a validation set where I hold back some of the information from my underlying system, and it cannot learn on that information, and then evaluating my performance on that instead. So when I repeat this test and include the validation set, it turns out, to begin with, this line right here shows my performance in the validation set. My performance continues to improve. It doesn't improve as much as it does for the training set, and then suddenly it starts getting worse and worse and worse again. So I end up here on this portion of the curve at the end. And this is one example of one of the most common mistakes in machine learning, which is called overfitting, where you're training a model that works really, really well on your training set, and then you try applying it to new data, and it completely fails to generalize to that new data. Furthermore, this also highlights something else that might be an issue with this. Even the best performing model on my validation set here, which is a training epoch of about 25, isn't doing that great. It still has an error rate of about 22%. So I have go through, train this system again, in this case to account for the overfitting by introducing an epoch where I stop it early at. Another approach would be simply to regularize my system or introduce a regularization parameter. And then I feed the system or a picture of my dog to the system again, load up a picture of Luna, and see what I get. Once again, my system says cat. So this goes back to the point earlier I said that my validation set error isn't actually that great. So the next step, I have a hypothesis. Maybe I don't actually have enough information to train a good system. In order to test that, I'll create a lot of different training sets randomly according to the training set size and see how my model performance looks as I vary my training set size from about 25 to 200. Sorry, to 400 on the x-axis. Then the y-axis, again, shows my error rate. Then to begin with, I can't learn very much at all from 25 pictures, and I start learning and start learning and start learning. But I notice that I'm still learning by the time I hit 400 pictures. So this simply tells me I need more data, or if I add more data into the system, it's very likely that I'll improve my results. So this is an example of data insufficiency. And for a lot of problems in the world, throwing more data about the underlying problem generates better results, especially for things related to computer vision or speech recognition, where the underlying phenomena creating the data is incredibly complex. So in this case, I go back to my photographer friend. I ask him to send me not just a couple months of his pictures, but years and years of them, load those up, and train my new model on those. And now I see I get a pretty good performance where my validation error rate drops close to perfect. So once again, I load up one of my test cases, picture of Luna, throw it in. In this case, my system worked. It says that my dog is in fact a dog. But I take a picture of another of my dogs, Stella, load up a picture of her, throw it through my system, and turns out my system made a mistake. It says she's a cat this time. So what on earth went wrong? Now I go back and I actually look at the training data. A machine learning system is only as good as the underlying data that you're putting through it. In this case, I noticed that my photographer friend Adam, he had a habit of every time he did a photo shoot of a dog, it was outside, usually in the grass. And every time he did a photo shoot of a cat, it was inside. So my system, instead of learning dog versus cat, it was actually learning grass versus carpet or inside versus outside. So it completely failed to generalize when I threw it a new concept, a dog, and on the inside of the house on carpet. So this is an example of both generalization error and another really pernicious phenomena in machine learning known as data leakage, where information that's irrelevant to the prediction you're making, in this case, whether or not the picture was inside or outside, followed through the model and ultimately caused it to make a wrong prediction. So now I realize that my photographer friend's no longer sufficient as a data source. I'll go through and download a dogs and cats data set, blow the new data set into a memory and train it, and then I'll see what happens on this test case again, and this time it gets its correct. So loading in dogs and cats in a lot more different contexts helped improve and fix the system. Now, I'm pretty confident my system's working well. I'm going to take it and put this prototype into production in my house on a prototype system that Sarah sent over. And then to begin with, it works. My cat Zodi's really happy that he can come inside now through it. And then about half an hour later, I hear a really funny sound downstairs. I go downstairs. I see my system just let a raccoon in. So I'm thinking, what on earth is going on? Why am I getting a raccoon in my house? My raccoon's not a cat. I take a picture of a raccoon. I throw it in through the system. And naturally, it's calling a raccoon a cat. And this is a very extreme example of a non-stationary distribution. So prior to this point in time, according to my model, the entire world consisted of dogs and cats. It had no concept of raccoons or other animals or even an empty sidewalk. So my system wasn't built to handle exceptions like these that would very naturally arise in real-world situations. So I go through, I downloaded another class that from a bunch of random images online and use that to model anything that's not a dog or a cat, then train a new system based on that. And now I'm pretty confident that I have a system that works a bit better. It goes well on all my offline metrics, so I go ahead and send the model back to Sarah for her to test in her house. And at first it works initially really well. I get a phone call back about half an hour later saying it let her cat in. Her cat was really happy to be able to come in independently, now and not sit at the door meowing. But then some time passes. About 2 hours later, I get a really, really frantic phone call from her saying, my system let the entire neighborhood of cats into her house. So it turns out I was going about this solving entirely the wrong problem. I thought I was building a dogs versus cats detector. Instead, she did originally want me to build a system that was a pet recognition system that says, yes, this is my cat, and it can come into the house. And this is an example of another really common error in machine learning, which is solving the wrong problem from the first place. And usually, whenever you're training a machine learning system, there's some mismatch between the system you're training and the ultimate business goal that you're trying to solve. In some cases, it's unavoidable. In others, it can be really severe, like in this extremely subdialized example. Well, that wraps up this initial hypothetical case study. And now I actually want to move on to some real-world examples of the gremlins that we've seen, most commonly across hundreds of machine learning projects. So the first one I mentioned earlier is a really pernicious phenomenon known as data leakage. In one paper on data leakage specifically, it was deemed one of the top 10 data mining mistakes. And essentially, it's the introduction of information about the variable you're trying to predict that's not legitimately available to your system. And then machine learning models are really, really good at identifying single variables or combinations of variables that relate to your final target value. So if it's in there, your machine learning algorithm will depend on it to make predictions and thus be either incorrect or less robust. And one example where we've seen this arise before is in a prostate cancer data set that we have that came in with hundreds and hundreds of different variables related to the patient and the patient's history and various other outcomes. And we went through, we trained a system based on this, and what was hidden in here was one little variable right here in the middle called prostate. Now, it turns out that this variable was entirely predictive almost of whether or not the patient had prostate cancer because it represented whether or not they'd had prostate cancer surgery in the past. So, naturally, it's very, very useful if you're trying to train a system that, or in making a machine learning model that looks good on paper, but it's completely useless if you're actually applying it in a clinical situation. Then, one of the issues that we wrestle with on a daily basis is this statement also appeared in that paper. The concept of identifying and harnessing leakage has been openly addressed as one of the 3 key aspects for winning data mining competitions. And from our experience, that's definitely true, and that's one thing we try really hard to avoid, launching a competition that has significant amounts of leakage in. And then the best way to do that is anytime you're training a machine learning model, going through and peeling back the magic and looking how it's working under the covers to see what are the most important variables my model's using to make predictions based on, number one. And secondly, how is it actually using those variables? Or what's the partial plot or the relates between that underlying variable and the target value, and asking, does this make sense? And should this model be behaving in this way? And that brings us to another of our gremlins, which I mentioned earlier, overfitting. Then as a reminder, overfitting occurs where, as in this example here, you're trying to split between the blue dots and the red dots. There's 2 possible models. There's this black line here, which represents how the data was generated, plus a noise term. And then this is the boundary that you ultimately should be learning. And then an overfit model, instead of learning that, we'll learn this green line here, which fits the training set perfectly, but doesn't generalize as well to new data points as the other model. And this is illustrative in 2 dimensions, and in 100 or 1,000 dimensions, moving to a very high dimensional space. It's the difference between a model that performs really well and a model that completely fails to perform. And then one way to avoid it is paying very close attention to your training error versus your validation error, or techniques such as k-fold cross-validation. Now, we also see this arising in some of our competitions in different contexts. Since when we put a competition up on our site, people can get feedback on one portion of the test data set, what we call the public leaderboard set, but they don't get feedback on another portion of the data set, the private leaderboard set. So we see here the correlation between those 2 scores. On this axis, and in this case, a lower score is better. We have a score where they did get feedback on, and on this axis, we have a score where they didn't. We notice that mostly they're correlated, except in the very top performers, it becomes uncorrelated, which means that it can look like you're doing the best on a given problem, but actually some other person is. So it results in a leaderboard shuffling at the end of the competition. And this is a pretty moderate example. In a more extreme example of this, apologies for the coloring, this is a bit harder to see on this screen, but we have the public leaderboard performance over time for the top public score on the public leaderboard here, and the private leaderboard performance over time for the best score on the private leaderboard, which the participants weren't aware of here. And then in this case, again, lower is better. And one interesting thing about this is that about a third of the way into this, the true generalization error stopped improving. So this was the best score. It hit a plateau. However, people kept overfitting and overfitting and overfitting and overfitting on the public leaderboard. So they kept looking like they're doing better and better because there's a human in the loop. They're either directly or indirectly incorporating feedback from that public leaderboard into training their models. And that actually doesn't carry over when that's applied in the real world. So it's not only the case that overfitting can arise when you're training an individual model, but also a collection of models or any time that you have a human in the feedback loop. Furthermore, John Langford, one of the famous machine learning researchers, went through and outlined a couple of the ways he'd seen overfitting before. And it's important to realize that this can occur at every level of abstraction in machine learning, from an individual machine learning problem to, instead of when you're trying to show that a machine learning method works well, choosing a data set that shows that method works well out of all the possible data sets as opposed to vice versa, or choosing a metric that shows your system works well, or even into publishing, if a reviewer is looking at 3 or 4 different papers, choosing the paper that did best on the given data set to let it through the review process. And then that brings us to one of the third most common gremlins, when you focus on data set sampling and splitting. So how do you actually sample your data set for training and test purposes when you're going through the process of evaluating a machine learning model? Now, one example of where this went wrong was one competition that we hosted with Wikipedia. They constructed a stratified sample of the set. The competition was around predicting churn for Wikipedia editors, and it turns out that even rows represented editors that churned, and the odd rows that represented editors that did not churn. And this information ultimately was leaked through to the participants, and it resulted in some of their methods, or at least one team's methods, picking up on that discrepancy and then winning the competition, not just because they were able to pick out which ones were likely to churn or not, but also because they discovered this feature, which is an example of both a leakage error and a dataset sampling or splitting error. And it really reinforces the point that various machine learning algorithms, once you throw a given dataset at them, they can be really, really good at picking out any discrepancies in there or any form of leakage in there. And this is another story from a machine learning engineer at another company. I can't share the context around it, but I can share the outcome. They'd been working on a time series modeling problem where they used a week of training data and a week of test data, and for a while they'd been working with logistic regression. That he tells me that they tried a random forest instead of logistic regression, and then it improved their performance by 14%. And this is at a problem where a 14% performance improvement is big and relates back to their revenue. So it's like, we're going to be rich. But it turns out, instead of training on 1 week and testing on the next week, they're actually overlapping that week by 1 day. So there was a 13-day period, not a 14-day period. And random forests, which are an incredibly flexible model that are given the chance to overfit, are capable of overfitting, perfectly fit that 1 day overlap in there, which corresponds to a 1/7 performance improvement or 14% improvement. Then that bug had been in the code for years, but until there was a flexible model thrown at it that was able to take advantage of it, it wasn't obvious or it wasn't realized. So that brings us to another point about time series, and that properly testing time series is incredibly tricky. A lot of times, if you don't have the infrastructure in place to run a full back test, so running your model forward through time and feeding every data point in as you would have gotten it, you're basically making a trade-off between overfitting to a single point in time, throwing all your data set before that point in time into training, all of it afterwards into test, or randomly taking chunks and setting a week of time as training, a week of time as test, and vice versa, and then allowing some future information to leak into the past or be involved in predicting the past. And one example of where there's another issue with time series, this is with a bond trade pricing challenge we worked on, where we're using time series in increments of 12, so each row corresponds to 12 data points. It turns out when we received this data set initially, it wasn't one row corresponding to the first 12, then one row corresponding to the next 12, or numbers 13 to 24. It was one row corresponding to data points 1 through 12, the next row corresponding to data points 2 through 13. So it passed an initial test for not having very many issues. But it turns out that when a participant went in and ran a model that, instead of looking at the previous 12 data points, only looked at the previous 3 or 4 and took the nearest neighbor, it was able to fit this perfectly because all that information already existed in the training set. And a final thing to watch out for around splitting data into training and test sets. For most real-world data sets, various quality issues can fold into them. For example, if you're working with essays, then maybe an essay got entered twice into your data set, so you have 2 examples of that, not one. Then those can randomly fall into training and tests separately, which causes you to overestimate your true performance. So it's another useful check simply to go through to make sure you don't have any duplicate rows in your data set. Let's see. Then the final point around that is one rule of thumb that I found works really well is before you're training a model on a set or really diving deeply into it, check that the ID column isn't informative. Because many cases, due to sampling or other issues, it'll come out back, yes, the ID column is actually very informative or even perfectly informative about your target variable. And that can also be an issue for some stochastic machine learning models, even if it's not a fundamental issue, because they're trained by taking it one data point at a time if they're being trained in an online fashion. And then there are cases where you'd expect that column to be informative. For example, if you're working with time series. So it's not always a problem, but in many cases it exposes other underlying issues. And that brings us to another issue that virtually every person that I've ever worked with around a machine learning problem has said something along the lines of, this data sucks, this data is really, really crappy, this data has a lot of different issues in it. I've never had someone come to me and said, this is a perfect data set for the problem that you're trying to focus on. And just for a couple examples of where that can arise, for one project that we did around predicting flight arrival times, we had in this case, some of these were entered by humans, and we had planes taking off before, or landing before they were taking off, or taking off before they left the gate, and so on. In the essay scoring competition, we also had an essay that said, this essay got good marks, but as far as I can tell, it's gibberish. And the humans rated that as an almost perfect essay. And it turns out that the person or the company that we're using to transcribe this didn't follow those transcription instructions perfectly. And in some cases, instead of throwing those essays out they couldn't read, they went ahead and just left comments like this in our data set. And probably the best way I know to find what quality issues are present in your data set, if you aren't aware of all the possibilities, is to throw it up as a machine learning problem and try writing a machine learning competition on it. Because there's nothing like having 100 people pour through it to identify everything wrong with it. For example, one of the most popular threads in our forums when we run a machine learning competition is the one that inevitably arises on data quality issues. And for example, in this case, this is a set involving bulldozers and basically developing a blue book for bulldozers or a pricing algorithm for used bulldozers. And it turns out a lot of them were apparently manufactured in the year 1000 because someone thought that made a good default value. Let's see, for the sake of time, I'm going to skip over this section. To wrap up, I did want to go ahead and highlight some of the choices, again, that you make when defining a machine learning problem. So you're making a lot of different decisions over the course of going from business process or business goal to a production system, including things like what data to use, what data not to use, what's your target variable going to be, how you're going to measure performance, and how are you both offline and online, how you're going to select your models, what production constraints are you operating under, such as time and memory, or how are you going to make model updates, or are there any language or platform constraints. And it's really useful when you're thinking through all these different issues that arise when defining a machine learning problem to also keep in mind the different gremlins that can pop up and try to proactively avoid those issues or make sure you're at least asking the right questions that make the issue as apparent as early in the process as possible. So that brings us towards the end of my talk. Again, I hope you're walking out with just the 3 simple messages from the beginning. First, that machine learning is powerful. Second, that we've gone through a very small number of the many, many ways you can mess up machine learning. And thirdly, these are avoidable just by asking a couple basic questions. Do these results make sense? What other data might my machine learning algorithm see that I'm not considering right now? And what's my generalization performance, or how does this apply to new data? So thanks a lot for taking the time to listen to me, and I also would really appreciate any feedback that you have on my talk. I have a little survey form up there for you to fill out. And I think I'm out of time for questions, but I'll be around Strata for the next 24 hours or so, and reach out to me directly if there's anything that you want to talk about. Thank you.